So let's go over the homework for week 4, actuators. What I want to do is not show you the answers, but talk to you about what to do about it. So I'm on Blackboard. I'm going to buzz down here to week 4, and we'll take a look at the homework. So as we can see, the homework can be handed in for 5 marks. Yeah, because I really need you to do this. I need you to delve into this deep and really get this stuff. And the exam is going to be based on this, or there'll be a lot of stuff on the exam from this. So let's continue. Let's actually take a look at the homework. I'm just going to walk through it, and we'll look at every single question. We'll talk about like how to do it, and actually we're going to jump into the PowerPoint. I am going to open up the PowerPoint, so I'm going to just do the PDF version so I can jump back and forth. Okay, so let's take a look at this. We've got an example here where we have an actuator on a brake. A brake is a cool device that actually bends metal, and that is, in this particular situation, it's activated and controlled with a pneumatic actuator. It looks pretty big if you take a look at it there. That's a large actuator, so it's got a lot of power to it. So what you need to do is you need to calculate the extension force and the retraction force. So the extension force actually, in this case, actually is going to be a lot more, or it's going to be required to be a lot more. The retraction force is not required as much because once you bend that metal, you're just opening the brake up again. You're not actually doing a lot of work. And that's okay because the retraction force will actually be less because the rod's in the way, so we have less area. Let's just take a look at that. So we're going to go buzz down here and take a look at that concept where we're looking at the forces. And in this case, the force has this whole area for extension because the rod's not in the way. But the force for retraction is going to be actually less because there's less area there. And that's okay because if we take a look at this, to press it this way is when you're bending, and then to pull it back is just kind of opening up the brake again to put new stuff in. So it's all right. So what you're going to do here is you're going to calculate this. You have the pressure that's being used. You know it's a 2.5-inch cylinder. I've given you the rod diameter, but you don't actually need it because it has nothing to do with extension. Okay, good. So for that, you just use this formula. What's wrong? Use this formula. You go in here, you know the pressure, and you know the diameter, and you kick it in here, and you calculate the force. So you're done. So you do need this because you need to calculate the force for retraction, although you don't really need it, but I'm making you calculate it. Okay, good. So there you go, and you're done. So pressure calculations. Essentially, you're gonna use the pressure is force times area, and you're going to look at that formula. You're going to solve for force, you're going to solve for pressure, and you're going to solve for area. Always solve your formula. Dude, if you really need to, like some of you guys need to do this, I need you to go over to documentation guidelines, and let's take a look at this. Okay, I don't want to see a formula that's got 2 equal signs on it, and I don't want to see like arrows or whatever. Dude, formulas look like this. You write the formula, or formulations look like this. You write the formula, you fill in the formula, and you write the answer. Equal sign, equal sign, equal sign, underneath each other. 3 steps, no more than that. Okay, good. So let's go back to this. All right. So isolate, sorry, the other thing, is in here? Yeah. Does it say this? Isolate your formula. Always isolate your formula for the unknown first. I don't even think I put this in here because I thought everybody just knew that. But yeah, so if you're solving for P, isolate P out of the formula. Write a new formula called P is whatever P equals to. Yeah, P is force over area actually. So that's easy. So isolate for P. In this case, P. So pressure calculations, pressure is force over area. That's going to be the formula. Underneath that formula, you're going to fill it in underneath that equal sign like this, like this, like this. Then you're going to write the answer. So in this case, it's pretty simple. You've got the information you need. And so what it's asking is you've got to calculate the required pressure to make this thing work. So this thing actually picks stuff up. It's pretty cool. It's got a vacuum cup on it. We will study vacuum at some point. So it grabs onto the thing and it pulls it up. Now, the weight, the heaviest part that it's going to pull up is going to be 100 pounds. So you've got to figure out how much force, how much pressure you need to create that force. But look at it. The actuator is going up and the force is being generated from this side, so from the rod side. So you've got to make sure that the area you use is the rod side area. Okay, good. So that's why I gave you the rod dimension here, 3/8 of an inch. So you're going to do that, and then actually, just some of you guys may have remembered this. I think you've studied dynamics. You must have, but if you haven't, doesn't matter. So you need to, if a weight if you have a weight that's 100 pounds and you're trying to pick it up, you need more than 100 pounds of force to pick it up. You only need 100 pounds of force to hold it there static, but if you're going to accelerate it, yeah, force is mass times acceleration. So if you're going to accelerate it, you need a little bit more force. So add 10%, just good engineering practice. But this calculation can be plus or minus 2 psi, whatever. So you're going to calculate some exact amount. You're going to, like, well, I need like 67.325 psi. Well, no, just whatever. 67.3, okay, whatever. So just go for like 70 or something like that. So I just said plus or minus 2. That's because like the answer is actually plus or minus 2. So just ballpark that and then actually add 10%. So in pneumatics, we're kind of ballparking things a lot. You're like, this is probably good enough, because in the end, you can actually adjust the pressure really accurately if you need to. It's pretty cool. So in this case, this is pretty cool. I built that. Who built that? Oh yeah, I built that. Yeah, my company built that. Actually, I physically built this. Okay, so this is really cool. You're selecting an actuator. So this actuator has got to actually push up, and it has to push with 20 pounds of force. So you've got your dimensions here, and you have to calculate, you have to choose the right cylinder. Actually, I've done a lot of this where I know how much force I need to generate, and I know my pressure range. I know I can work with like 30 to 35 psi, but let's just say you had 34 psi and you needed to apply 20 pounds of force. And your actuator, you're not dealing with the rod diameter of the actuator because it's an extension force, and you can see that from the picture. So you have to then calculate, or more specifically, yeah, you have to calculate the area that you need to make that happen. And then you've got to choose the right cylinder that's close to that area. So do you use a 1 inch? Oh, I don't know why there's a period there. There shouldn't be. There should be a comma there. Yeah. So do you choose a 1 inch, a 7/8 inch, 5/8, half? I can tell you the half is not enough. But you know what? You're going to calculate the area, and then you're going to say, hey, which one's close? And which one is close is okay. So you got to get it approximately. So that's why I like highlighted the word approximately. So 20 pounds. So if you actually ended up getting 19.7 pounds or 20.8 pounds, it's okay. Okay, good. So this is pretty cool, displacement of actuators. So in this section, you're calculating how much air is required to make the cylinder go out and return. And or you can look at it the other way. If you were to actually move the cylinder back and forth, how much air would go in and out of it? Either way, it's all the same. You don't have to look at it one way or the other. It's the volume of the cylinder, the volume inside the cylinder, the volume of retraction, and the volume of extension. So if you take a look at this, this is pretty cool. This is like a trap door that just like opens and closes and allows flour to fall through from a silo down into a mixing area or a cauldron. So what's going to happen is that this will open for a certain amount of time, flour will fall and it'll shut. So you need actually a lot of force to do that, because you really got to go into that grain, and the grain's really falling, and or sometimes it's not grain, sometimes it's flour. In this case, it is flour. So what you need to do here is you've got the dimensions of this. I don't know, for me, I always draw things. I would suggest you just draw the cylinder and label the dimensions. And then from there, you know the stroke and or more specifically, you know the rod travel. And in this case, the rod travel is the same as the stroke. And if we go back to the slides, like have these open. Okay. So we're going to extension, displacement, retraction. Okay, so actuator, extension, and retraction. So what I want to do is go back to, this is the timing. There's a spot here that talks about rod travel. So rod travel, in this case, is the clamping distance. But the rod travel is how far the rod moves during operation. It's not the stroke. Actually, sometimes it is the stroke, but it doesn't mean that it is the stroke. So in this particular application, the rod travel is the stroke. So this cylinder goes all the way and all the way back. Let me get a cylinder. So the rod travel may be just this and that. So that's how much air is going in and out of these ports. During operation, this thing just does this much. That's it. That's the rod travel. But the actual stroke is this. This guy is a 15-inch stroke. So this can go 15 inches, but in operation, it actually only goes this far. So that's the rod travel. So in this application here, on the computer here, in your homework, the rod travel actually is the stroke, because that's designed to go all the way out and all the way back. I don't actually know what that mechanism, how that mechanism works, but I'm just assuming that that's what's going on. So what you're going to do is you're going to calculate this. You're going to find the two areas. We'll go back here to the PDF. We get it. Okay, so you're going to find this area and that area. And that area is there. There's the formula for the area. There's the formula for that area. And then you know the rod travel, it's 14 inches. And then you can just do your calculations. And the calculations, if you need to go and you can look here. The calculation for displacement for extension is this. The calculation for displacement for retraction is this. And you can use this formula because you know this information and you know that information. So just continue with that and write it down, and it's good. Similar as rod travel, 10 inches. Okay, so here, these are just the dimensions. This one's easy. Just go to this formula, use this formula and that formula, fill in the numbers, and press play. You're done. Okay, cool. Timing. What you need to do is you really need to wrap your head around this. And I've actually made this kind of a long and detailed going on and on description. And these kind of things happen. So when we're engineering and we're designing things for other people, you get a description of the process. So someone will say, okay, this process is going to do this, and the cylinder is going to go out, and then the part's going to come in, and then someone's actually going to put, the robot's going to put something into the part or do something to the part. That'll take about 4 seconds, and then the cylinder has to retract. And you may say, does the cylinder, what you may think about this application, you may say the cylinder should actually get out of the way really quickly. Like, whoa! So retract really quickly. Or maybe if the cylinder is pushing something, you may want to slow it down. You want the cylinder kind of push it slowly. You don't want the cylinder to just go like, whoa, bam, and smash into it. So you may say, okay, the cylinder is extending slowly, but retracting quickly. I have to put that into my timing calculations. If we want to talk about time, the reason that we need time, again, we're looking at flow rate. Essentially, all of this system here is working. They're actuators that are going and doing stuff, and we have to run them. They displace a certain amount of air. We want to know the rate at which we displace the air. However you calculate rate, you need time. So we need to know how much air this displaces in how many seconds. Well, we're not going to calculate how much air all of these things displace. Actually, one of the questions later just kind of gives you the air and gets you to actually calculate the CFM. But in this case, I want to know how long all of this takes. I think it's this question that you have to calculate the displacement. Well, one of these. So read this. Try and unpack it. So an automated sliding door in a CNC machine. Okay, that's cool. So it's a sliding door, it goes back and forth. So there's a pneumatic actuator that makes that happen. On the door, there are 2 pneumatic locks. Okay, the locks are just small. I'll show you how big they are. All right, they're really tiny. Take a look. Okay, so they're actually probably even smaller than this. So this guy just goes bam, bam. Now, it's a lock, so it doesn't actually have to even move this far. So the rod travel may be like this. So bam, 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 bam. And it'll be quick. So the timing of this is almost instantaneous. So we don't actually have to add that timing into the cycle. Not if we've got other times that are like 3 or 4 or 5 or 8 seconds, like a 1/10 of a second or a 1/4 of a second for this thing to move back and forth. We don't really need to put that in. Okay, let's just continue here. Okay, there are 2 of these that lock the door back and forth. Okay, so as soon as these guys lock, so the door is closed, and as soon as they close, it just goes bam, and it locks. 2 of them. So they lock, and then actually just wait a second. So just make sure everything's okay. The door's locked, everything's good. Let's actually start the next process. So after the door locks, 1 second after the door locks, a long pneumatic actuator retracts slowly, unlocks. So as soon as the door unlocks, maybe it's like that's unlocked, then the door slowly opens. Takes 3 seconds. The cylinder's just not going to go like wham and like rip the door open. You're going to meter it a little bit to go slowly. So it'll slowly open. It takes about 3 seconds to open. And then from there, a robot. So it opens and it just sits there, waits for the robot. The robot goes in and it grabs the part. sorry, the robot goes in, yeah, and it removes the part, and then it goes, picks up another part. So it removes a part, picks up another part, and then puts the part back in. How long did that take? Well, that took 13 seconds. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7, 8. Okay, so altogether, and it says that, that's 8 seconds plus 5 seconds. So this cylinder, these guys went like this. They went like this. Bam, both of them, quickly, almost instantly, they did that. And then, right away, this thing started to open the door. Took 3 seconds to do it. And then, it sits around. Everything just pauses for 13 seconds. And then after that, what happens? Then the door, the robot picks up the aluminum block, plays in 8 seconds. Yeah, as soon as the robot's done, okay, as soon as the robot's done. So we know that takes 13 seconds for that to happen. The door automatically closes. Okay, so again, 1, 2, 3, the door is being closed. Okay, good. So the door is automatically closed. This takes 3 seconds. As soon as the door closes, the locking cylinders extend and lock the door. Bam. So again, that's just so instant. You don't have to put that into the timing. So you can add, maybe you can say a quarter second and then put that in. That's fine. You can do that. We're going to see that's not going to change the flow rate too much. But it's okay. You can put that in, but essentially you can forget it. Okay, good. As soon as the door, the extension retraction of the locking cylinders are almost instantaneous. Once the door is locked, the CNC starts to machine the parts for 20 seconds. So that's your turnaround time. That's your idle time. The 20 seconds is the idle time because this process happened. So this is how they started. Unlock. Open door. Pause for 13 seconds. Closed door. Let's say that's closed door. Closed door, 3 seconds. And then wait 20 seconds for everything to happen. And then start all over again. So do your timing chart. Now let's just go to the slides, the timing charts. I don't know what to call them. Timing charts or timing, I call them timing statements. Oh, whatever. So do your timing statement. So look at this. Like write down the control statement and then take a look at what action takes a certain amount of time and then the time between actions. In this case, 2 of the actions take 3 seconds. And then there's a lot of idle time between the action. So the second question is the same thing. You have to figure out the timing all of this. Again, it's a description of what's actually going on. So when you read this description, think about the timings that you need to know. So here, essentially, with the timing, what you're looking for is you're looking for the total time required for the sequence. So the sequence is A plus, B minus, A plus, whatever it is, that's the sequence. The total time for that. Now, there's time for each action and then the delay time between each action. And then there's the idle time. So there's the whole sequence time and then the idle time, and that in total is the whole control time. Or essentially what's going on is that we got to take a look from here all the way over to there, and that is the time for the entire cycle. So we've got the sequence time, which is A plus, B minus, A minus. That's the sequence time. There could be time in between the actions, and each action could take time. And then there's the delay time, or what I call kind of the turnaround time. And then there's the whole time, which is called the cycle time. So for that cycle to happen, how long does that take? Think about those things and look at these examples here. There's another example here. There's like I gave a lot of examples here. So really think about that and figure that out from here. Do the same thing here and figure that out. There's a 12-second delay in between and stuff. So this takes and there's actually a 30-second delay. That 30-second delay is probably the idle time. I forget. Let's just see what it is. Okay, as soon as the cylinder is retracted, the cylinder retracts, puts the box, the operator moves the box and places empty. This takes 30 seconds. Okay, the operator removes the box and places a new empty one in its place. Okay, so this box actually goes in. The box is being pushed in, and then something is placed in the box, and then the glue cylinders come out and glue it, and they kind of put the glue there, and then these 2 cylinders come in and like close the box and hold it for a certain amount of time, and then after that the box is retracted, and then an operator picks it up, puts it there, and a new guy does that, and that takes 30 seconds. So that 30 seconds is the idle time in between. Again, just look at the whole sequence. Look at the whole sequence and say, what is the whole sequence time? And then from there, look at the idle time, and then that's going to go over here. That's the whole cycle time. So the whole thing is the cycle time, and that's what you have to calculate. So just do that little chart. Do one of these little charts for this. The flow rate. Now, the flow rate questions are, the first one's a little bit more complicated, but what you really have to do here is you've got to do some area calculations and volume calculations, so that you've got to calculate how much air this thing uses to go out and retract. Okay, so a single cylinder in a manufacturing facility extends and retracts continuously, back and forth, back and forth, back and forth. So it takes 1 second to extend and 1.1 seconds to retract. Why is that? Well, because there's more force pushing it this way and less force pushing it this way. So actually it's going to move out a little bit more quickly than it will moving in back. Okay, depending on actually how much force, what it's doing when it moves out. So in this case, it's not really doing much work this way, it's not doing much work this way. However it is, it actually extends and retracts a little bit differently in timing. It could be that one is metered more than the other. The retraction is metered a little bit more. When it retracts, it waits. Okay, when it extends, okay, it extends, 1, 2, retracts, 1, 2, 3, 4, 5. We know that takes 1 second. That takes 1 second, that takes 1.1 seconds, and then there's an idle time in between. So you have all of the dimensions here, so you can calculate, and certainly the rod travel as well. You can calculate the displacement, no problem. And then you know the timing. Well, if you know the displacement for extension, displacement retraction, and you know the timing because you're going to do that little timing thing here. And then you can actually calculate the CFM, pardon me. And okay, so question 2. This is 1.2 cubic feet is the total displacement for all the cylinders during one sequence in question 3. Okay, so if we go up to here, question 3. So this was the question here. There are a lot of cylinders here. So actually they're up to F. So there are a lot of cylinders. So there, you're saying when all of those happen, like when the whole sequence happens, blah, 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 the air that is displaced during that entire thing is 1.2 cubic feet. There you go, 1.2 cubic feet. So you already know the timing for that. So it's pretty easy just to actually calculate the flow rate. So just do that. And then you're done. So the homework is done. So do that homework and hand it in. It's worth 5 marks. If I see that you guys are not following the proper documentation, I'm actually going to check all these and start to remove marks, because I've kind of had enough of people not following the proper mathematical, grammatical rules. And also, if you're doing it on a computer, please do not do this, and make sure to use your upper scripts, your postscripts, and your subscripts. And if you don't know how to do that, this tells you here how to do it. So follow these instructions here, or you can do the whole thing by hand. However you want to do it, that's fine with me. Oh, goodbye.